wrap up the minimax theory. And to remind you where we left off, this is the minimax risk, as we call it. The worst case risk, and then the minimum overall estimate. And what we saw was that if I just pick out two arbitrary distributions, P0 and P1, with parameter values theta 0 and theta 1, that the claim was that we had well, first of all, this quantity, first of all, I forgot to say this last time, is certainly bigger than or equal to, instead of taking the soup over the whole class, I'm now going to just take the maximum over those two distributions to a much smaller class. So this is bigger than this, so this is already a lower bound. But the key thing was that this thing, which we still don't know how to compute, I think is bigger than this formula, which is now something we can compute. It's just an integral. And this delta is just the distance between these two parameter values. And we saw there was a couple other ways to further bound this. For example, this is bigger than delta times e to the minus 10 times the go back logarithm. And I wrote another one in the notes last time in terms of full variations. So let's start by proving the key thing here is how do we prove this? And so the proof works like this. I'm going to use actually some of the stuff we did in the slide. First thing to notice is, let's imagine, let's pick any estimator in the world. Now I want to show you that no matter what estimator you pick, I can bound it like this. If it's true for any estimator, then it's true for the n. So you give me any estimator. I compute that estimator, let's say it's here. That estimator you can think of as defining a kind of a hypothesis test. Testing whether it's theta 0 or theta 1. If it's closer to theta 1, we declare theta 1. Over here, if it's closer to theta 0, we declare theta 0. So in other words, we can define, and by the way, I'm going to start by proving n equals to 1, so a single observation. That's a bit easier. So we define this function phi of x, which is, let's say, 1 or 0, depending on whether it's in this zone or this zone. So if your estimator is closer to theta 1 or 0, if the other way around. Of course, which one we call 0 and 1 here is kind of arbitrary. In fact, looking at it, I probably should call the label the other way, but anyway, it doesn't matter. I'm writing it this way because if you think about hypothesis testing, that's like a 1-0 thing, right? You either say, oh, the null is true, the alternative is true. At least for testing a simple hypothesis. So I'm converting it kind of a hypothesis testing thing. It's like I'm testing two simple hypotheses. Theta 0, theta 1. Notice theta hat doesn't have to be equal to either of these. I'm just saying which one's closer to. Okay. So now what we want to do is I'm going to show a simple bound on the distance between your estimator and the estimator. Let's consider two cases. Suppose the truth was P0. So suppose I actually generated the data from P0. And suppose phi turned out to be 1. Then, let's look at delta. Delta, in this case, I can say, well, delta, well, by that's the definition of delta. Now I'm just going to do the triangle inequality and put theta hat in here. So this is less than or equal to theta 0 and theta hat. And theta 1, theta hat. But, by assumption, oops. My comma sometimes looks like phi is, we're doing the case phi is 1, so theta hat theta 1 is less than theta say it's less than or equal to beta hat beta 0. So I'm going to get less than 2. Or in other words, say the other way around. In this case, clearly beta hat, the distance between beta hat and beta 0 is bigger than the delta over 2. I'm just saying something very obvious here, which is that if beta hat ends here, then beta hat has to be pretty far from beta 0, because these are at least delta apart. So what that means, though, is if I look at the mean, let's assume the truth of the moment is P0. So if I look at the mean distance between, well, suppose that the true distribution is P0 for the moment. The reason why I'm doing that is because we've reduced the calculation to computing this expected value over two distributions on its C0 and P1. So now I'm considering the P1 case. Certainly that's bigger than or equal to the expected value times an indicator function, because an indicator function is either 1, in which case it does nothing, or it's 0, which makes it small. And in particular, I mean the indicator. However, this is exactly what we just computed. When P0 is true and phi is equal to 1, we just said that this distance is bigger than delta over 2. So in this case, this is bigger than delta over 2. So this is bigger than or equal to delta over 2 times the expected value under P0 of this. Well, what's the expected value of an indicator? It's just the probability. Right? It's just the probability. Let's just be clear what I'm doing intuitively. All I'm saying is if P0 is true, the expected distance is bigger than or equal to the distance between these times the probability of choosing the wrong one. That's all. And of course, we can argue analogously for the other case and conclude that under P1, the expected distance between beta hat and the truth is bigger than or equal to delta 2 times the probability under P1 of choosing the wrong one, which will be phi equals to 0. So the expected distance of the estimator to the truth is bigger than or equal to the distance between the two things times the probability of choosing the wrong one. It's similar. Well, hence, this supreme number is bigger than or equal to this max. But this maximum is simply the maximum over P0 and P1, what we just computed. It's simply the maximum of this and the maximum of this. Therefore, the mean max risk is bigger than or equal to the maximum of this quantity. So we just concluded, let's call this R. That R is bigger than or equal to the maximum of those two things I just computed. That is delta over 2 times the maximum of I think I've switched phi on you. This is supposed to be the error probability. So I'm sorry, I realize there's a typo there. This should have been 0, 1, and I should have followed that through. Right. Because what this is supposed to be is the probability of making a mistake. And I mislabeled phi at the beginning, and then I started labeling it correctly. I should have defined phi to be 0 when you're picking out theta 0 and 1 when you're picking out theta 1. That would have made much more sense. And at some point, I started doing that. Right up here. So just to be clear, though, let me just clarify that. The minimax risk is bigger than the half distance between the hypotheses times the maximum probability of error. Probability of error means truth is P0, it's the probability of saying no, it was theta 1. And the error, if the truth is P1, then the mistake is saying that it was 0. So again, I apologize. I think this should have been 0, 1, and then you have is that apart from the error? I hope it's clear what's going on. It's just we've reduced the minimax risk to the distribution hypothesis and the maximum probability of picking the wrong hypothesis. Probably picking the wrong hypothesis on this, the wrong hypothesis on this one. I'm not sure it's an error. That's not an error. Does it look okay? Something looked funny to me. Okay, good. No error. Somehow it was backwards for a minute, but anyway. Okay, good, good. But what are we going to do about this max? Well, we're going to use a very simple trick. The maximum of two non-negative numbers is bigger than or equal to their average. So this is bigger than or equal to the average of those numbers. So now I'm going to get probably delta over 4, because I'm going to take a half of that. 4 times probability I just took that 1/2 there. Okay. So let's picture this. Like I've got two density functions, P0, P1. I've really kind of reduced it to a hypothesis testing problem. I give you an observation and you guess whether it comes P0 or P1. And I'm adding the two errors together. Probability of thinking this one when the truth is here and vice versa. What method or what is the optimal thing? How do I minimize the sum of these two errors? If you think about one as a type 1 error and a type 2 error, I know someone's thinking it. Feel the thought ways. I'm just trying to say it.
Name and Pearson.
Name and Pearson amount. Now actually, you probably learned it in a slightly different form, which was to fix the type 1 error and maximize its power. But it's also true that if you try to minimize the sum of the errors under each hypothesis, the name and Pearson limit tells you that the optimal test is to just pick the maximum of the densities. So the name and Pearson test minimizes this. Again, you probably did the proof for fixed alpha, but you can check that the proof also works for the sum of the errors, and it tells you the name and Pearson test. What is the name and Pearson test? It says that the optimal test, the minimum, to minimize this, you choose 0 or 1, depending on the value of the density at that point. So for P0, in other words, you look at the likelihood ratio, you look and say, here's X, here, let's say X is here. You say, which density is bigger? Oh, P0, I'll call it 0. But if it was over here, you would say 1. You just take the ratio of the densities, and whichever one is bigger, P0 or P1, tells you whether to choose P0 or 1. That's the optimal test. That minimizes the sum of the errors. Since it minimizes it, we therefore conclude this is bigger than or equal to the probability of the error under the name and Pearson test. Oops. See, what we've done is gone from, you gave me an arbitrary estimator, theta hat. Could be any estimator. I don't even know how you got it. That defined implicitly some test phi, and I have no idea how it's meant to be a very complicated function. But I know that its risk, or its probability, is bigger than a particular test. And now for this particular test, we can work this out very easily. Because let's look at this. What's the probability of an error under P0. So let's imagine you draw from P0. When would you make an error? You're always going to declare 0 when P0 is higher. But if you happen to draw a point here, then you'd make an error, right? So this would be the integral of P0 over the region where P0 unfortunately is less than P1. That's the first probability right there, right? That's the probability of getting the Damon Pearson test, shooting out a 1, saying you're in this zone, when you actually drew from P0. So when you get into P0. And similarly, the other error is just P1 of X over the region when P1 is less than P0. In fact, if you think about it, these are disjoint regions. I'm just integrating over this region and this region. I'm integrating this over here where P0 is the minimum, and I'm integrating this over here where P1 is the minimum. This is exactly equal to the minimum of P0 and P1. Set out to prove. The only thing is I did this for n equals to 1, so I didn't have to carry around these product, this is laziness really, product densities everywhere. Everything I just said would be true for n observations. The only thing that would happen is you replace the density P with the product density, for n observations. So I should have just done the proof in general n right at the beginning. But all that happens is those are raised to the power n. That is, remember what I mean by that, P0 to the n. We're really talking about the product P0 over xi, I equals 1 to n, similarly for P1. And that proves the first statement. That proves that the one that's in the box. So it really came down to saying that the expected error, well, first the soup over the whole class is bigger than the maximum over any 2. And then the expected error is bigger than or equal to the distance between them times the maximum probability of error. And that's minimized by the Damon Pearson test. Then I said there was other bounds, like I said this was bigger than or equal to 1 minus the total variation distance, the 2n, or bigger than or equal to the KL1. Let's just prove the one I put up there. So let's prove that this thing, which is called the affinity, is bigger than the KL distance. First of all, I hope let's remind ourselves what the KL distance is. It's the integral between two densities. One nice thing about KL distance is that the distance between the KL distance based on n draws is n times the KL distance for a single draw. That just comes from the definition. You just plug in the product measure as the KL distance. So that's why that should really be the KL distance between P0 to the n and P1 to the n. Then I use this property to get the n up front. But I still have to relate what's the KL distance even for one observation. How does that relate to the affinity? So let's prove. It's worth seeing this kind of proof once. So let's take, there's the affinity for one observation. So that's just P of x and P of x. Is bigger than or equal to half P minus KL. And as I mentioned in the last class, the appendix to these notes lists a whole bunch of distances and a whole bunch of relationships between them. So, I don't want to prove all those. It's going to days doing that. Let's just do one. This proof is a little bit non-obvious. It's kind of a slick proof, so it's a good one to do. So it works like this. First of all, the first thing to notice is I claim that if I take P max, that's the maximum of P into Q, plus the integral of the minimum. That's exactly equal to 2. You can see that by writing that as the integral wherever P is bigger than Q, and dividing it up into one where P is less than Q, summing up the two integrals, and adding it all together. And you get exactly the integral of P plus Q. So is that clear, or should I leave that? Maybe I'll just do this. So I'm going to, in other words, I'm going to put these all into one integral. And now I'm going to break it up. Let's say A is the part where, I don't know, P is bigger than Q, let's say. And I'm going to break this integral up over A and A complement. And so that's the integral over A. Well, if P is bigger than Q, then that's the max. But over here, it's the opposite. So it's P plus Q. And similarly, over A complement, I get Q plus Q. Now I put it back together, and I have P over the whole A and Q over there. Times integral P plus Q. Okay. So now, what we're going to do is the following. Starting with that fact, we do the following thing. We say, first of all, let's take 2. We want to prove this, so I'm actually going to bring the 2 over here. So 2 times P bigger than Q is bigger than or equal to. If I subtract anything from 2, then I make it smaller. Oh, question again.
I don't think it's the integral of P plus Q, right? Not 2 times.
Pardon me?
Isn't it just the integral of P plus Q?
What did I do wrong?
No, it's in the same class. Because it's over 2 different sets of
Oh, yeah, this one, right. Yes, thank you. And then we get to this. Thanks. Okay, so I'm just going to make this smaller by taking 2 minus something. Something convenient, namely 2 minus integral of P max. So in oh no, yeah, right. Good. I'm just taking 2 minus something, so it's smaller. But 2 minus the minimum is exactly the maximum. So that's the integral P max Q times the integral P min Q. All right, and now I claim this is bigger than or equal to the integral P max Q times P min Q. Square root all squared. Why is that? Because it goes in shorts. It goes this way. This is less than. But now you can see this is always, again, either P is bigger than Q or Q is bigger than P. So if P is bigger than Q, then you're going to get one of them. You get P is bigger than Q, then this minimum Q. And this one is P, and conversely. So no matter what X you're at, this thing is actually just square root of P times Q. Right? There are 2 cases here. P is bigger than Q, Q is bigger than Q. Either way, this thing is P times Q or P times Q. 2 times P. 2 times Q. 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 2 times make this look, somehow I'll get a log in here, and the only way to ever do that, I know, is to e to something. I guess I take e to the log of this. And so we get e to the 2 log integral here, which actually it's going to be helpful to rewrite this. Let me rewrite this as p square root of q. That's the same thing. I haven't changed it. Now I want to bring the log on the inside, so I'm going to claim that this is bigger. Oh, there's a typo. There's 2 logs in the next expression. There should only be 1 log. So this should be e to the 2 times p times log q over p. Why was I able to do that? Switch the log through. Expected value, the log is the log of the expected value. Intensity equality. And this is a 1/2, right? Log of 1/2, I can bring 1/2 of so this is e to the integral p log. Whoops. Oh yeah, that's good. Q over q. But if I make that q over q to the minus, it worked out. A miracle. I'm sure that was going to work, but it did. Okay. And again, there's millions of relationships like this in your consistency, so they're usually much easier to prove than this. A lot of them are pretty obvious. All right, now let's prove finally a minimax rate. Let's do the regression problem. That seems to always be a warning you need to get moving. Does that happen at the same time? Third class? Right before 2 o'clock? So what we're going to do, so now I'm on the bottom of page 849. We'll do a special case. So I'm going to make the model a little bit simpler than necessary just to make the calculations easier. These calculations can sometimes be a little messy. So I'm just going to simplify things a bit. We're going to take regression data, we're doing non-parametric regression. But to keep it simple, I'm just going to assume this has a uniform 0, 1. This is not necessary, but again, this makes the calculation much cleaner. And we're going to assume that y is some smooth function plus epsilon. And again, to make the calculations easy, I'm going to assume the epsilons are all 0, 1. This way you get a flavor for how the calculations are done. Don't have to go through a lot of grief. If you start letting x have an arbitrary density, y more epsilon more general distribution, you can still do these calculations, but they just become a problem. But we need to make an assumption about m, and I'm going to do one of the simplest ones. But we're going to assume that the regression function satisfies the Lipschitz condition. So it's a set of all m's such that x and y is less than or equal to L times x minus y for all x. And notice the Cron's lemma is about distributions. And we do have a joint distribution. And the distribution is the distribution for, there's actually 2 random variables, x and y. Although in this case, you can write that as p of y given x and p of x. I made x uniform just to make life easy, so that's p of y given x. And because epsilon, let's look at y given x. This is just normal with mean m, right? So this is actually all right. Normal mean m of x variance 1. So well, I should put the density. I'm is a density. So let's write the density. So really the class of distributions are the class of all joint densities where the marginal is uniform and the conditional distribution y given x has a normal form and where this function lies in this class. And all we need to do is pick two arbitrary distributions in this class and hit it with Laplace's lemma. And I mentioned in the last class that we're just going to pick an inspired guess. Oh, what are we estimating? So if we tried to estimate the whole function in L2 error, it turns out Laplace's lemma is not powerful enough to give us the Newman down. We have to use Stanhope's lemma for that. Instead, I want to focus on estimating m at one point. Let's just say, how well can I estimate m at 0, let's say. It doesn't have to be 0, you can pick any point. So we're focusing on how well can I estimate this function at a particular point. The question of how well can I estimate the whole function in L2 error, again, we have to use a slightly different lemma called Stanhope's lemma, but we'll just do this. All right, but I have to pick two functions. And as I said, I'm going to just say, well, let's take the function 0. That's in the class. That's a Lipschitz function. That one seems pretty easy. And then the idea is to try to pick the alternative, if you think of it like a testing problem, to be something similar. And something similar is going to look like this. So the formula then is, right there, it's L 0. So this is epsilon. And when x is 0, this is my L epsilon. So there's kind of a tuning parameter in here, epsilon. I fix it epsilon. And then I've kind of tried to find a function which is Lipschitz as close as possible to the M0 function. It has to be Lipschitz to stay in the class. If we were doing, twice the differential functions, we might have to use it on cover and things would be smoother. Is that clear then? So my two distributions are E0 xy will be of course, the x part's uniform, so it's just 5y minus m0 x, and m1. Well, what epsilon would it be? Well, that's the good thing is I can fool around with that and get it to come out to be the way I want it to be. So according to Laplace's lemma, the minimax risk is bigger than or equal to, it was, I'll remind you what it was. What was it? It was delta over 8, e to the minus m, and then we go back to y with distance, is that right? I think that's right. Let's figure out what delta is. Delta is theta 1 minus theta 0. I'm going to use the absolute value scale here. But what's theta? Theta is the function value at 0. So under m0, that's 0, and under m1, that's 1. So this is equal to all right, so the risk, let me actually put that in here. This is the only thing left to compute is the tail distance. That's just doing an integral, and it's simple, but it's a bit tedious, so I'm not going to do it. It's the plot of page 850. It just ends up being an integrated. Well, what you see I've done there is to go back loud, maybe I should say a couple words about it. put in the definition of KL distance. But you can see that the x parts are all going to go away, right? Because the x parts are all uniform. All I'm left with is the normal part. I'm just left with an integral at the end, integrating over only y. The x drops out. And so I end up with integrating the Kovac-Weiler distance between two normals, actually. So I wrote it like this. The Kovac-Weiler distance between normal 0, 1 and then normal actually, I switched the integral from the numerator. So let me say that again. The P0, x, P1 of x, P0 of x, they're 1. When that goes away. When I integrate over y, I'm just left with these, the Kovac-Weiler distance between two normals. So that's what I'm writing, the Kovac-Weiler distance. And then at the end, you have to integrate over x. But the Kovac-Weiler distance between two normals, if you don't know, is just when they have the same variance, it's just the difference between the square root of 2. So this is the difference of m1 of x times m0 of x squared over 2. And now we just plug in, m0 is 0, m1 is this function, and I worked it out there. It turns out to be L squared epsilon cubed over 6. So we could plug that in here now, but there's still this epsilon. So let me tell you the trick, is you're always going to end up with a tuning parameter when you do these things like that. But you want to make, I mentioned this last class, you want to make KL to be about of order 1 over n, so that this becomes like a constant. That's usually the right way to do these things. So I chose, if I set this to be, in fact, there's a corollary right in here where I said a good choice of both KL distances to make it the convenience log 2 over n. The log 2 is not so, it's just a convenient constant. The key is that it's 1 over n. Now I can solve for epsilon. And what you get is epsilon has to be 6 log 2 all over L squared n to the 1/3. And we're done. I just plug in epsilon here and here. But by the choice of epsilon, this becomes like a constant. It's really this epsilon that's going to give you the rate. So when I plug this in here, into the KL, and I plug it in here and in here, it's just algebra. It turns out to be some constant over n to the 1/3. Is there any questions so far? I hope you can see that once you kind of guess at the two things, it's just kind of grinding through some calculations and plugging in at this point. However, how do I know that's a good, is that good? Is that round type? Maybe that's a really bad lower bound. We still have to find an upper bound. And how do we find an upper bound? We take any estimator and compute its risk. I don't know, did we do the Lipschitz case? Yes. So do you remember which Lipschitz, which non-parametric regression estimator, well actually there's more than one. We can pick any estimator one. I'm just going to pick the simplest one, the regressigram, or the regression version of the histogram. If you divide the, I guess we did the kernel too, but anyway. I think that was one too. Did we do the kernel? Yeah, but anyway, I think we did the kernel actually. But we picked an estimator for the Lipschitz case when we first did non-parametric regression. And we worked out the risk. So we found an estimator whose risk It might not be the one I said it out. There is an estimator, let's say the kernel estimator, such that the expected value of n hat at 0 minus m of 0, that's just, what is that? Well, let's first of all do the, we did it in terms of squared error, right? Which was the bias squared plus the variance. But you can actually do it in terms of the absolute loss, which I'm not really sure why I chose absolute loss here. And it's, so if you look back at the notes, you'll probably see 2/3, but that's because I did squared error. Here I'm doing absolute error. So what we've just shown is that the risk, if you have an upper bound and a lower bound, let's say this one is one constant. I haven't kept track of the constants here. But in terms of rate, we've solved the problem. The mini-max risk is order 1 over n to the 1/3. If I had done it in squared error, which I don't know why I didn't do that, but if I had, of course, everything would be, so this is for absolute, this is for absolute squared, which would be much more in tune with how we've been doing everything in the course. That's probably what I should have done. It would have been exactly the same calculation, everything would have just been squared. Maybe that's better what I should have done. So we get 2/3. And in fact, if you try this in d dimensions, you have to think a little bit about what the two functions would be. It's not that different. So you have to picture a function, you know, one function will be like a table. This is the 0 function. And the other one will be some sort of Lipschitz perturbation like at the corner of the table, or maybe a little pyramid in the middle of the table. And I'm not going to do that, but you'll see you get in that case, again, instead of, let's do it on the squared scale, squared error, it'll be 2 plus d. Which, yeah, means 1 gives you 2/3. So you can imagine that calculation. A little bit more onerous to do the KL distance, that's all. It's pretty much the only thing that is a little bit of calculating. But it's not that bad, actually. The key is to think of a simple function and a simple function plus a perturbation. That's the way to think about it. Make sure the perturbation is simple enough that you can do calculations in it, that it's pretty close to the original function, and that it's in the function class. It has to begin with class here soon. Then you crank through the calculations, and hopefully there's a free parameter which you play around to make the KL distance like an order 1 over n. And then you get the rate. And then hopefully you also know an estimator which achieves the upper bound. So that's the Collins method. That's an example of how we use it. It's actually used all the time to do a lot of complicated problems with that. It's good when you want to compare like a function at a particular point or some scalar quantity like that. That's when we're using the function. So I'm going to move on then to Fano's method. But let me see, are there any questions about that? Now that you've seen that calculation, I can assure you that anything you can expect to look at will just look like a much more complicated version of exactly what you do. Well, we want to move on to Fano's inequality. So Fano's inequality, if I wanted to do this example with this loss function, like for example, squared error or something like that, where we're measuring the loss along the whole function. The column doesn't cut it. You need to use something a little bit more elaborate. Generally speaking, things that require measuring distances over a whole function or something like a whole object typically use Fano's inequality. There's other reasons for using Fano's inequality. A lot of times you don't know. Sometimes you try the Collins method, you try Cano's method, and you just try the different methods and see which one you sharpen down. But Cano's method basically does the following thing. You know, what we did was we reduced the problem to 2 points, P0 and P1. But you could imagine that in some problems I might be able to do a whole finite set of distributions, and I might get a better bound. And that's all that Cano's law is doing. It's doing morally the same thing as the Planck's lemma, but with many hypotheses instead of just one. So here's the theorem first, and then we'll briefly go through the proof. We can just do it quickly because it's not that much different. Suppose I take some finite set of distributions contained in my class. When we go to implement this, it's going to be, instead of looking at a function like this, you can imagine many different functions like that. Like there's one perturbation, here's another one. Here's another one. Or, here's another one, 2 bumps, right? You can imagine making lots of different perturbations, maybe different numbers of perturbations, so you can imagine creating a whole finite family of alternatives to that n0. That's what you should have in mind. Then, of course, the soup, again, the soup over all of P is bigger than or equal to the maximum over this finite set. So that is, let's say, first of all, bigger than or equal to the n times the maximum of P over this finite set. That's trivial. That's just because I replaced the big set with a smaller set. Now comes the actual lemma of interest, which I'll write in 2 ways. This is bigger than alpha over 2, 1 minus n beta whoops. This should be a capital N. This is not the sample size. This is the number of distributions I'm putting. Let me say what these quantities are. So that's the answer. There's 2 numbers in here, beta and alpha. Beta is like what we called delta before. So here's my finite set. Alpha is just looking at the distance between beta pj So if there was only 2, that would be what we call delta, which is the distance between. But now we're looking at the minimum distance between all. Beta is the maximum of the pullback Leibniz distances. Now this expression might be a little bit hard to parse, so I'm going to now show you a corollary, which is how we actually use this in practice. In practice, we usually try to find a bunch of sets, a bunch of distributions. So again, to make this kind of like 1 over n, except that there's going to be a log term involved in the number of hypotheses. So the key is, we usually try to choose, suppose, so let me state it as a corollary. This is corollary 3628. This is exactly the same result, but I'm going to make a particular choice for beta. Suppose I can find a finite set of distributions such that the maximum pullback Leibniz distance is about 1 over n away. And we saw how to do that in our example. So the corollary says, suppose you can choose P1 to Pn such that beta is less than log n think of it again as above order 1 over n. Except now there's a log term which comes from the fact that you have many hypotheses, not just one. Then that formula simplifies. We look at the risk is bigger than or equal to alpha over 4. Very simple. That comes just from inserting the data in there. So this is how we actually implement it. We'll do an example in a few minutes. I want to make sure the theorem's clear though. It's the same as the Poisson, except instead of 2 hypotheses, we get finitely many. We get this kind of cumbersome expression. If we pick the KL distances just right, it simplifies then in the corollary. Just alpha over 4, because all this becomes bigger than half. And alpha, again, is just closest pair. So I'll just go through the proof now. It's pretty short. Any questions? This is very powerful. This is between Fanon and the column you can almost make a career of even getting that state. Right? So the proof we can do pretty quickly because it's very similar to the previous proof. If we say, let's take any estimator, again, an arbitrary estimator, and again, you can think about that as a hypothesis testing point of view that I'm choosing one of the finitely many, that is the closest one. That is, define z to be the integer which tells me is theta hat closer to the, this one, this one, this one, and this one. So it's the argmin over j of the distance so it's just the closest dot. It's just like the line. And arguing like we did in Macron, we know then that the expected distance is bigger than or equal to the distance between the guys and the probability of error. So mimicking that idea, we have that for each j, the expected value under pj of the distance between this arbitrary estimator, theta j, is bigger than or equal to alpha over 2 times the probability of an error, which in this case means the probability that z is not equal to 0. I hope you can see the parallel there with it's just the multiple testing. So our z is, it's really like multiple testing. The z is not moving between 2 hypotheses, it's choosing between n hypotheses. And so if I take the max again over j, I get that the maximum over all these finitely many of this expected value here is bigger than or equal to alpha over 2 times the maximum over j of an error. You've given me a random variable which guesses which distribution generated data, and I'm going to each of those p's what's the probability of error, and I get the maximum, and I do exactly the same trick. The maximum is bigger than the sum. If you're wondering what the connection is with the stuff you did 705 with Bayes, it's right there. This is like saying I'm saying that the maximum risk is bigger than Bayes risk over a uniform file over this finite set. But replacing the maximum over the sum is similar to what we did in 705 when we go prior down to get rid of the maximum. It's replacing a maximum with an average. That didn't mean anything. Alpha over 2. I'm just saying the maximum is bigger than the average. And when we only had 2 hypotheses, we bounded this using Neyman Pearson lemma. For n hypotheses, we use an information theoretic quantity called itself requires a proof, which I'm not going to go through. It's not difficult, but it's a bit long, and it's in the appendix if you're curious. So I'm just going to state it now. This average probability of error has exactly the form that I stated. It's 1 minus n data plus which completes the proof. So the one piece of hard work I admitted was going from here to here, which again was Neyman Pearson for 2, it's Fano's lemma for more than 2, proofs in the back, it's an information theoretic proof. But the proof strategy, I think you can see, is exactly the same as in the Tom case.
This is powerful because you can choose first alpha and beta, and then you can choose your PJ.
This is powerful because you can actually get a lot of minimax to solve a lot of problems with this technique. It's probably the most commonly used method of proving it. So let's actually see how to do this now. Because the one part I didn't tell you about was how to pick this set F. And we have to be a little bit careful, it turns out, about this, because sometimes the obvious way of picking F doesn't quite work. And there's an extra trick, which sometimes gets kind of hidden away, but it's very important. I call it pruning. And what you do is you pick the set F in a very natural way to start with, and then you prune it. And let me explain what I'm talking about. You don't always have to do this, but you often have to do it. Okay, so what I mean is that when I go to do the regression problem, we're going to take M0, and now I'm going to create this finite set of alternative functions. Not just one, but many. I mean, let's say one could look like this again. Another one might look like this, this, and then this. Another one could look like this. You can think of there being many, many possible alternatives. These can be expressed in the form of what's called a hypercube. That is, F is going to take the following form. This is F, our finite set of distributions. For W varying in some set, well, omega varying in some set of omega, where what this is you can think of these are binary, let's say down to W down. So take a look at all these alternatives that I just created. What you can think about, what I'm doing is, I'm taking the axis, I divide it into some number of pieces, 1, 2, let's say, n. That's one of your tuning parameters, n. You're going to have to figure out the right number of chunks. And then what the omega is it's like an on or off. If it's on, I'll put a bump there. If it's off, I'll put a 0. I'll just keep it 0. So you can see if I give you a string of bits, 0, 0, 1, 0, 0, 0, then I'm going to get, and I think putting a little perturbation whenever there's a 1 or not, that gives me the set of functions that I'm going to use, the finite set of functions. And in principle, we'd be done now. I've just told you the finite set of functions, and we just apply Fano's inequalities. That doesn't quite work. So this is called a hypercube, right? If I let this vary for each omega j between 0, 1, that's just the hypercube 0, 1 to the power n. The problem is that's a little bit too filled out. What do I mean by that? I mean, remember we have to compute alpha, which is, what is the minimum distance of any function in this class? And the problem is, if they only differ by 1 bit, so let's look at this function. Let's suppose there's 1, 2, 3, 4, 5, and let's suppose I have the same function. The problem is, the L2 distance between them really only is very small. They only differ by 1 bit. The L2 distance will be small, and that lower bound is not going to be very big. So the question is, if I think of all functions like this, is it possible for me to discard some of them so that any pair of these functions is pretty far apart, and yet I still have lots of functions? It's an interesting question. Let me say it again. So I'm going to take the hypercube, all these bits, zeros and ones. Each one generates a function that looks something like this. I notice that, sometimes they're really close together. That alpha gets really small. I don't want it to be small. I want the lower bound to be as big as possible. Can I prune it? Can I say, I'll prune this one out? Like I can start with this function and then say, I'm going to throw away anything that's too close to this one. And in fact, this is what prune works. This pruning thing, operation, you basically pick one out, throw anything away that's too close. Pick out another one, throw away anything too close. Can I do that? And still have lots of functions. You still need lots of functions for this to work. The answer is yes, surprisingly. It's called this famous theorem. It's right here, 3633. I'm going to tell you what it says. It's called the Bar-Shamov-Gilbert. And I won't put the proof, but it's actually just uses hook-taking inequality. It literally does what I just said. It does a greedy construction combined with hook-taking inequality. But let me just tell you what the result is. It's possible to prune this hypercube. So what am I going to call the pruned one? I'll call it omega prime. So I'm taking a subset of all binary strings of length m. I'm now throwing away some, but I claim the following, that I can choose this subset such that 2 things are true. The number of them, let's say m is the number of guys in here, that I want to make sure I'm not throwing away too many. And in fact, m is bigger than or equal to, it turns out, 2 to the m, 2 to the, what am I calling this? Let's say m. So remember the original thing, how many things were in here? 2 to the m, right? I'm now doing this pruning operation. Now there's 2 to the m over 8. That's not much smaller. There's still lots of functions. But the distance between any of these binary strings, how do you measure the distance between 2 binary strings? The Hamming distance, right? You just count how many entries they disagree on. So to find the Hamming distance between 2 strings to be just the number of entries where they differ. That's just the Hamming distance. That's just the number of, if I give you 2 binary strings, count how many places they differ. That's the Hamming distance. The problem we had originally was that the Hamming distance could be as small as 1, which would result in the 2 functions being close. In this prune set, it turns out that the Hamming distance for any pair in here is of order m. That's kind of surprising at first, right? That I can make any pair of them about m away. And remember, there's m slots. That's going to be great, right? Because now that means any pair of functions, they're going to differ in at least m spots. So their L2 distance is going to be big. And yet, I still have a pretty rich class of functions, which is going to make it all work out when we now do the minimax calculation. Let me just back up though, and guys do a lot of action and make sure it's clear. And start up.
Why does the proof not use something?
Oh, well, I don't really want to spend time going through the proof. It's kind of clever and unexpected.
It doesn't seem like a probability anywhere.
It's one of these cases where it's a combinatorial thing, and you end up counting something. And then when you look at the counting thing, you say, oh, that thing, that combinatorial term can be thought of as the probability that a Bernoulli satisfies certain properties. How do we do that? We can bound that with hook-taking inequality. So it's kind of like a probabilistic method being used. Because you're right, it doesn't seem at all like a probabilistic thing. It's just a handy way to do to bound a certain combinatorial. Any other questions? Everybody with me? Okay, so I want to now go back to our regression example and finish it in L2 distance using this trick. So we're going to do exactly the same class. In fact, if you look at page 853, this example, I even do it more generally now. We're allowing it to be beta smooth. So we're going to allow it to have beta, two smooth derivatives, three smooth derivatives, whatever. And the function class, again, I'm going to take it to be uniform on X just to make the calculation simple. So we're just doing the plain old beta smooth class of functions, and the set of regression functions again is I'm going to take this hypercube parameter, it's called omega again, and all I'm going to do is put those, this is again a string, this is the binary string we talked about. It's either on or off, and I'm going to stick a little perturbation in that slot, just like I talked about. The only difference is I'm going to require phi to be, let's say we're doing a class of functions with two smooth derivatives. We require it to be a function with two smooth derivatives. And the exact construction, did I even give it? Yeah, I even wrote down for you what such a function looks like. You just basically take a nice kernel and you squeeze it a little bit. And now the key is we're not taking all such things, we're not taking all omegas, we're taking them in the true hypercube. And now we're almost done, because what do I have to do? Banow's lemma says I need to just get the KL distance between any of these two distributions and the L2 distance. The L2 distance is pretty easy. If I have two functions like this, I just have anywhere where they're both 0, it doesn't matter, and anywhere where they're both 1, it doesn't matter. So I just got to count how many places they differ times the integral of one of these bumps. So that's done for you there. I'll just tell you what it comes out to. This is the simple integral. That the L2 distance, so I'm using L2 here, is bigger than or equal to the square root, because it's not L2 squared here, of the Hamming distance. That's just counting how many spots they differ. Times L, well, times a constant, let's not go back. And there's an H in here. What is H? H is part of the construction of this function. H is like a kernel times, so these functions are basically like H to the beta times some kernel. And we know that thanks to the pruning operation, this is at least m over 8. So this is bigger than h to the beta plus a half. And how did I choose m? It turns out a good choice, you'll have to trust me, is to take h to be 1 over m. I'm linking them together, in other words, as two units of m. And this turns out to be like h to the beta. With h still a free parameter that we're going to choose. We had two parameters to pick. The thing in front of the phi function and the size of the thing. I linked them together so there's only one parameter to pick because I knew ahead of time I could do that. And the KL distance again is a simple integral. I'll just tell you that it turns out to be h to the 2 beta. And remember, what did we decide? To use Banow's inequality, we said we pick the maximum KL distance to be something like log n over 4n. Is our choice. That's usually the choice that works. So now, but what is n here? N is the number of functions m over 8, which is equal to m over 32 n times log 2. And m I chose to be 1 over h. I know I'm going quickly here.
What's the small n times?
Sample size. Remember that in the columns of our chromosome there was an n. Sample size. We're done. I've just told you how to pick h. So now I can plug, I know what alpha is now because alpha is this. I know what the tail distance is. I plug it all into Fano's inequality. You can check this at home while you're watching Game of Thrones, and you will see that you get, and once again, for some reason, I did this on the square root. I didn't do the square, I did the L2 distance. This is the L2 distance, not the L2 distance squared. Anyway, I'm just plugging into Fano's inequality now, and with those choices, and you get C over n to the beta over 2 beta plus 1. Maybe if I'd done it on the squared scale, it would have looked more familiar because then we have a 2 here. And I hope that looks familiar, right? You've seen that many times in this class. If we had done it in d dimensions, it would be a d here. Exactly the rate we've been computing over and over in the class. And in fact, you don't really need uniform, just any smooth density on x words. You made lots of simplifying assumptions here. Yeah, I went through this pretty quick. So you should go through it again. But the strategy is very, very general. You just take some simple function, make little perturbations of it, maybe prune it a bit, like we did, prune it here. Then it's just a matter of compute the distance between every pair of functions in your class, that's alpha. Compute the KL distance between each pair, or bound it, you can't compute it. Set that KL distance to be something like this, which will now fix any tuning parameters for you. Stick it all into that Fano's inequality, and out comes a rate. And again, we know this rate is tight because we showed you that there's many things like kernels and squads and everything that achieve this rate. So the upper bound is this rate too. So we've got a matching lower and upper bound. So review that at home, but it's pretty. We've covered a lot of territory. These two things, the column and Fano, possibly with the pruning step, can solve 98% of all numeric. I just made that number up, but it's probably very close. Okay, yeah?
So, how big can the constants get, and can I?
That's a good point. So in a lot of this stuff, it's very hard to keep track of the constants, especially in really complicated problems, and they can sometimes be pretty big. And plus, you don't know if you've optimized. Maybe I could have done a better job. So typically, people don't worry about it. They really just want to figure out that I at least get the right rate. There are certain classes of problems where you can be very exact about the constants, and that tends to be normal problems. So
could you use the constant to choose which method might be better in practice?
you know, to be honest, once you get down to the level of constants, I'm not sure how much information you really get. What you really want to see is if your estimator is converting at the wrong rate, then that suggests you could really improve your estimated problem. If it's just the constants, then you don't know. You know, I have to do 10,000 approximations to do this, and so people don't usually worry about the constants so much. There's like a bunch of Russian guys who spent years figuring out the constants in certain problems, and it's really beautiful mathematics and everything like that. But in practice, I'm not sure how much that really matters. And maybe there's some counterexamples to what I'm saying, but generally speaking, we don't want to do much of it. So that concludes this part. There's a lot more in the things, and I just want to tell you what's there if you're interested. If you're not interested, you now know enough minimax theory for this class. Okay? You know enough minimax theory to get to most of this theory. That's sort of how I try to do it. But if you're interested in what's in here, there's a little bit about maximum likelihood, and there's some more examples, like I use density estimation. There's a surprising one about classification, which is worth looking at if you're interested. That for a long time, people noticed that classifiers seem to work much better than minimax theory predicted it should. And I think the best explanation of that, which I review in here, is what's called Sivakhov's low noise condition. There's a certain condition which says basically the two classes are fairly well separated, which seems to happen a lot in practice, even in high-dimensional cases. And the minimax theory, when you incorporate that, shows that indeed you get very, very fast rates of convergence in minimax theory, even in high dimensions. So it explains, in some sense, why classification can work so well in high dimensions. So there's a section on that. There's a section about semi-supervised learning. There's a lot of other little goodies there that, again, if you're interested, enjoy it. If you're sick of the minimax theory at this point, you just stop there and consider that all to be something that you're reading one day. Okay, so that's, to summarize, we'll go on Fanon. Those are the two main takeaways from all this minimax theory. Any questions about this stuff? If you can do that one example we did, you understand most of it. You understand the basics. Next week, Brian's going to start talking about some more convex optimization stuff. First of all, I posted an update of the previous notes that Ryan had on convex optimization. Can they download the revised notes? Or that's a typo? This is a typo. But there's also a second set of notes up now called what do you call it? Optimal rates in convex optimization. And that will be what Ryan goes over next week, so you want to make sure you read